right. So this notation that I've used here, this triangle, if you notice when I draw this triangle, I make that little extra bar over there. Did you notice that?
Yeah.
That's to make it bold-faced. Now, I think last time, or not last time, but one time I talked about this and decided to call it the del operator. Short for delta, and D stands for derivative. And so this is like some sort of derivative operator. And if we look at this abstractly as a vector, we can look at this as a vector of operators that would operate on a function of several variables by taking the derivative of that function with respect to x, y, and z. So we can think of this as a vector, and then now we can take a look at the two main types of functions that we're studying and apply those functions to this. And one of them we've already done. So we have a scalar function f. Now let's go 3 dimensions since we're talking about this in 3D. We can think about a scalar function f as a scalar function. And so the idea of a scalar multiplication means we have a vector and the scalar being multiplied together, except this is not multiplication because this is an operation. And for this we've seen before as the gradient. Actually, I'll switch notations in the middle on you guys because you all understand this already. And this is what we know of as the gradient.
Does the gradient not have the bold-faced up to that point?
It does. That's what this is.
Right. But, okay. So when did we not have the bold-faced up to that point?
For gradient, we did. If we just took a look at f itself and then decide we want to take the derivative of that with respect to x or y or z, then that's just a regular partial derivative. And that was not, that by itself is not the gradient. And if we want to collect all the different partial derivatives and make a vector out of them, now we have a gradient. And that's what we have here. Okay?
Why did you make it a point at the very beginning that this is bold?
Because I wanted to consider it as a vector. So vectors are either boldface or have arrows on top. And so I wanted to treat it like it was a vector. Okay? All right. So we had a scalar function, and really the only thing we could do with that scalar function is scalar multiplication. If we multiply a scalar times a vector, this is essentially what we would get. And this is something that we've gotten before. So today, we're going to apply the del operator to vector fields, which is a vector. And we saw back in, I don't know what chapter, but we saw when we started dealing with vectors that there's two types of vector operations, vector multiplications, right? We have the dot product and the cross product. So we'll consider that. with a vector field. So now if you have a function that takes 3 variables, x, y, and z, and outputs 3 components, so capital F is essentially P in the I direction, Q in the J direction, and R in the Q in the J direction, and R in the K direction. And they're all functions of x, y, and z's, then we have a vector field. So should I use IJK, or can I just use these brackets? Does it matter? Brackets are okay. Then we have a vector field, and so that is now a vector with 3 functions, P, Q, and R, and we can apply the del operator to that via the 2 different multiplications that we've learned. So let's first do the dot product. Where we take our del operator and then we dot it with a vector field. So what is our result there? Our result is taking this P function and taking the derivative of the P function with respect to x. Is the result going to be a vector or scalar? Scalar. So I drew those vector brackets, but I have to take that out because it's just going to be a scalar. So it's the derivative of P with respect to x, and then we add it, right? Plus the derivative of Q with respect to y, plus a derivative of R with respect to z. Okay? So this is called the div. And the div is short for divergence. And we'll see later on why this is called the divergence. So this, by the way, back in the old days when there was not any good typesetting things, and so drawing this upside down triangle was hard to draw on a typewriter. They just typed in div F. Have you guys ever seen a typewriter before? And so the other operation that we could do with vectors in terms of vector multiplication is the cross. So if we take our vector PQR and cross it with our del operator, oh, this one's a little bit more complicated. I think I started to do this last time and I just stopped. Ran out of time, I think. I don't just quit. Yeah, okay, sometimes I just quit. But a cross product is going to result in a vector. So we need to come up with a vector here. And I suppose we should formally cross it. So I, J, K, and then the partials with respect to x, the partial with respect to y, the partial with respect to z, and then the p, the q, and the r. So I'll write it down here because it's going to be long. With respect to I need to take the derivative of r with respect to y, dr dy minus dq dz. And the next term is a negative j. And cross out the j, I need to take the derivative of r with respect to x minus the derivative of p with respect to z. And then with respect to k, the k component is the derivative of q with respect to x minus the derivative of p with respect to y. I don't know. Yes. The k-hat looks like Green's theorem. I didn't want to do that yet. But that's what I was about.
Sorry, I gave you 10 seconds.
Well, we'll take a closer look at that later on. Let's absorb the div and the curl first. Div and curl. All right, now that it's all absorbed, let's do some examples. Let's find some vector fields to div and to curl. So by the way, div and curl by themselves is just, it's just like taking a derivative, except it has a special format. One of them is a dot product of sorts. The other one's a cross product. So it's really not that big of a deal. The bigger deal is understanding what it actually means and then applying it to the integral theorems that we're going to have. So let's, well, none of these are red. Let's pick one. Pick number 1. I was going to look at number 2. That looked a little bit, I guess it doesn't matter. I'll pick number 2. Who knows? Maybe they're both just as difficult, I'm sure. I mean, both just as easy. So let's do number 2. Yeah? 16.5. All right, let's take the div of this first one. So the div of this is, the div is the easier one. If you haven't, just like the dot product is easier than cross product. So we're going to take, we're doing number 2. We're going to take the first component of the vector field and take the derivative of that with respect to x. So the derivative of that with respect to x looks like it's just y squared z cubed. And that's it. Plus the derivative of the second component with respect to y. it's just going to be x cubed z squared plus the derivative of the last one with respect to z, x squared y cubed. And then we're done. That's it. And it's a scalar function, right? There's no ij's, k's here. We can look at this as just a function of x, y, and z. So it just describes it's a scalar value. Yeah?
What's the significance of the number?
The significance of the number.
Yeah. Are we doing?
How's it different?
What?
Are we doing it because we can, or is there
Well, both. We're doing it because we can. It tells you a number. The divergence tells you the divergence. So this is on a vector field, right? So imagine that you're on a vector field. And as you move along and follow the arrows in the vector field, you could be expanding or contracting, expanding or compressing based on the vector field. So if the vector field just goes all in one direction, then you're just humming along, going along in one direction. But if you go in the direction and the vector field expands, then you're going to expand with the vector field. So that expansion is like the divergence. Yeah?
So is the magnitude of this the expansion or contraction?
Yeah, well, this is a scalar value, so we don't need to take the magnitude. If it's a positive number, then you're expanding as you're passing through that point. If it's a negative number, then you're contracting. Okay.
Is it on a certain path?
It has to follow the certain path of the vector field. Whatever the vector field is has a particular path that you're following. Yeah. If you jump from one arrow to the other, you're going in the direction of the arrow, right? So you're just going to follow the arrows. Is that visual? Okay.
Are you jumping in at like a certain point? Isn't it kind of depending on where you drop in on the vector field?
Well, it depends. Yeah, it depends on where you drop in. But once you dropped in the vector field, then you have to follow a path.
So any path you have is going to have a div that equals that.
Yes. At any point on the path. And any path, yeah. Yeah?
So I'm not understanding the whole I'm myself and expanding or contracting. So is it just like the vectors are going inward as opposed to outward?
Yeah.
Okay. Okay.
But the vector field is known in the straight path. There's no Div and Curl, right? So it's a straight path.
If it goes in a straight path, then if it's not expanding, then maybe the div is 0. If it is expanding, the div is positive, and if it's contracting, then the div is negative. Yeah.
Is it the field arrows themselves, if they're converging or diverging?
Yeah. So let's see if we can.
Like in one part of the graph, they go toward like the origin, but then when they come out of the origin,
Yeah.
then it would be.
So at each point, you'll have a different div.
Oh, okay. I got it. No.
Oh, this one I can't change again. Oh, it just.
Good job.
So the path over here See these, if I pick a point here, I'm going to have to follow a specific path. And then the path will just go. Again, we didn't talk about that. That wasn't in the section in the book. It was in the exercises in the first section in this chapter. Now, I thought about talking about it, but I think it's a little bit more pertinent in differential equations than it is here, so I kind of skipped it. But that's what it is. You're following a specific path on a vector field. And then once you follow that path, depending on if these vectors are expanding or contracting, that's when your div is going to be positive or negative. So in this particular case, this is only 2 dimensions, but we can still take the div as something that's 2 dimensions. X and Y, what's the div of this vector field? Positive 2, right? So it looks like our size is going to be expanding as we follow anywhere on this path, and that's what's happening. Okay. So that's like the geometric interpretation of the div. Now let's take a look at the curl. So this one will take a little bit more work. So this is my vector field, x, y squared, z cubed, x cubed, y, z squared, x squared, y cubed, z. And then I want the partial with respect to x, with respect to y, with respect to z as my cross product. So the first term here is going to be the derivative of the last component with respect to y. So that's 3x squared y squared z minus a derivative of this with respect to z, the second term. So that's 2x cubed yz. So that's one of them. The second one, I'll throw a negative in front of that, and then take the derivative of the last component with respect to x. That's 2x y cubed z minus, and then the derivative of the first component with respect to z. That'll be 3x y squared z squared. That's my second component of my curl, and my last component of my curl is going to be the derivative of the second term, the second component with respect to x. That's 3x squared y z squared minus the derivative of the first component with respect to y, 2x y z cubed. So that's my curl. What does it mean? Okay. The curl is, in the past, I guess, was usually referred to as the rot, which stands for what? Yeah. So, rot, rotation. So it stands for the rotation. And what that means is that with the same idea, I guess we'll do this in the next page since we've started to talk about it already. So the div takes an object follows a path, and then measures the divergence or measures the increase in size or decrease in size as you move along the particular path. That's the div. The curl follows a path. I need to be careful here now. It measures how the path rotates. Okay? So in a path that goes like this, in this particular example, this is our vector field, right? It's just two-dimensional, so it's x and y. If we take the curl of that, we take the derivative, curl of two-dimensional. Let's pretend to take the curl of it. The curl is going to be 0. Did you get that? No? Okay. What? So imagine this. Again, I was going to do this later. So imagine, just like in the 3D graphing plotter thing, it's actually three-dimensional, but if we just let the third component be 0, then we're all good, just two-dimensional. And then if you take the curl of that, it's going to be 0, 0, and then the derivative of y with respect to x minus the derivative of x with respect to y, which is going to be 0. It turns out to be 0 anyways. So the point is that if you drop this thing onto this flow, it's not going to turn at all. So the curl is going to be 0. On the other hand, if you have a different if you have one of these things where you dropped that coin around, and you'll have to follow the path that it's taking you. So I tried to make it a little bit obvious here, but it looks like this thing is turning, right? It looks like this thing is rotating. So this has a significant curl to it. Yeah?
So it rotates and follows.
If you follow the vector, the whole idea, the whole premise here in our story is that we have to follow a vector path. Okay, so once you're following a vector path, we ask, does it turn? Does it get bigger? So that's what's happening. Yeah?
How does crossing it?
Oh.
Oh no.
Like
Yeah,
what?
how does crossing talk about this? Like it does talk about rotation, but how does it show it like with vectors here on the image? Yeah, but
Huh.
it's probably related to like torque, but.
Okay, so in this example that we came up with, I'll call it negative y comma x, I think. And if we take the curl of that, again, we have to assume that it's 0 in the third component. So let's rewrite this as negative y, x, and 0. And then let's take the curl of that. The curl of this is going to be 0 and 0. This 0 in the third component makes a bunch of zeros. because the functions don't have any z's in them, and then there's zeros here. So again, we'll take a closer look at that later. But the third component here is going to be the derivative of y, the derivative of what? No. All right, let's actually spend some time doing this. So it's I, j, k, partial x, partial y, partial z, and then we have a minus y, a positive x, and a 0. Oh. So this is where the first two terms will disappear. You'll see it disappear. The first term is the derivative of 0 with respect to y minus the derivative of x with respect to z. And the second term is the negative j, the derivative of 0 with respect to x, and then the derivative of negative y with respect to z. And then the last term is the derivative of x with respect to x minus the derivative of y with respect to y, negative. So the curl here just turns out to be 0, 0, 2, which is a constant. And it's also a vector, right? It's a vector. This is a two-dimensional picture, but we're pretending it's in 3D. How does the vector 0, 0, 2 look like? It's coming out of the page, right? So let's see if we can do this. I'm pretending to be that graphing program. So this is a two-dimensional picture, but I'm looking at it from a 3D point of view. These arrows here are all flat on the xy plane. These circles over here are also all flat on the xy plane. And it's following that flow line, right? So this cross product, or this curl that we found, are these vectors pointing up. They are rotating. I guess I should use my right hand. They're rotating, and they're rotating in the direction of the right-hand rule. So with a positive rotation, with a positive k component like this, your vector is going straight up. That means it's rotating in a counterclockwise direction as you're going along the flow line. So this can easily, or not easily, be seen in 3 dimensions. If you have a flow in 3 dimensions, a field, a vector field, a water flow, electronic field, force field, something, if you have some sort of field in 3 dimensions, you want to find the rotation of something in that field, then you put this thing over there, and depending on how it tilts and which way your curl is pointing, that's going to be the direction of the rotation using the right-hand rule. Okay? So the curl measures the rotation. Not only does it measure the rotation, how fast it's rotating, but it also tells you the direction in which it's rotating, because it's a vector, right? And the vector, using the right-hand rule, just put your thumb where the curl is, and then that tells you how something is rotating. And the magnitude of that tells you how fast it's rotating. Okay? How fast it's rotating. The magnitude of the curl.
So it'll tell you like the angular velocity of it?
The magnitude of the curl would be able to tell you that. So I got a couple of silly not popping up. Oh, here it goes. This is me rotating. So I have a positive rotation on that one. This one I couldn't get the vector field going for some reason. But this is me expanding. So I have a positive div there as I follow the flow line. I lost the arrows for some reason, so imagine that this is the vector field that we were looking at, the x and y, just expanding. So those are a couple of silly visuals. The center of rotation is where the point is. So each of these things, normally this would be a function. You just happen to have constant here. But let's take a look at this example. And this is going to be hard to visualize because this vector field is kind of difficult to visualize. But if you imagine this vector field at the point 3, 4, 5. So you have a vector field at the point 3, 4, 5 that's somewhere over here. And then you calculate your curl and you put 3, 4, 5 in for x, y, and z. And then say you calculated the curl and you got the curl to be something like this. Then that tells you at that point, so you can imagine that you would probably want this to be your center point of that disk that's rotating, and then your arrow comes out like this. So using the right-hand rule, it looks like we're rotating in this direction, and given that I kind of randomly drew this arrow kind of long, that means the rotation's probably pretty fast at that point. Yeah?
If you took the derivative of the curl, would that give you how fast you're accelerating? Or how fast you would be rotationally accelerating?
So the derivative of the curl. Now, what do you mean by derivative? So the curl is a vector field, right?
I guess that goes back to the original question, which was if you take the derivative of the vector field of velocity field, would you get an acceleration field? But now I see.
Yeah. So there's issues with the different types of derivatives now because we're dealing with this different type of function, the vector function, the vector field. We have to be careful about derivatives now. We have to be specific about what derivative do we mean. Do we mean a gradient? Do we mean a div? Or do we mean the curl? So now we have 3 things to consider. They can be combined, though. Let's take a look at let's take a look at a scalar function. So when I draw this, I mean this is a scalar function. That means this is f as a function of x, y, z that goes from R3 to R or R2. And what is this? Gradient, div, or curl? It's a gradient, right? There's no other choice. You can't do div or curl because f is a scalar function. So we know that this is a vector, fx, fy, and fz. Now that we know that, well, this is a vector field. It's a gradient field, but it's a vector field. Now let's do something interesting. Because this is a vector, we can actually take the curl of this as well. Oh, we could take the div of it, but we can also take the curl of this, right? Well, let's do both. Let's do the div first. If I take the div of this, I'm going to take the derivative of the first function with respect to x, right? This is a scalar. The div is a scalar. So I'll take the derivative of the first function, that's the first function, with respect to x, and then plus the derivative of the second function with respect to y, and then the derivative of the third function with respect to z. So that's the div of a gradient. And what's the result? Is it a vector or a scalar? It's a scalar function, right? There's no commas, components, or anything like that to scalar function. All right, well, that was neat. Let's take that same vector field and take the curl of this. I, j, k, partial with respect to x, with respect to y, with respect to z, and then fx, fy, fz. So in the I direction, this is a curl, so this is a vector field. In the I direction, I take the derivative of fz with respect to y, minus the derivative of fy with respect to z. All right, let's go to the next one. The derivative of fz with respect to x minus the derivative of fx with respect to z. And then derivative of fy with respect to x minus the derivative of fx with respect to y. So if this is a nice function, which in most cases we're going to be dealing with nice functions, these are mixed order, second order partial derivatives. And if they're nice functions, they should all be equal to each other. Which means the curl of a gradient is 0. Yeah. That means, what's conservative? The gradient field is conservative. Yes. So the curl of a gradient field. Now, I put 0 over here, but if you put 0 just like that, then that might be considered incorrect. Because the curl is a vector, and so we want to make sure that we differentiate from a 0 scalar versus a 0 vector. And since in the past we know that, well, we don't know that. This is, wait, how do we jump to that conclusion that this is conservative?
You start off with the gradient.
Oh. I guess if we want to be more precise, is a conservative vector field. Just to reiterate that a gradient is actually a vector field. Yeah.
So this is what you're talking about when you said we don't have a test
Now we do, yeah. So if you take any vector field, capital F, and you take the curl of that, and you get 0, that must mean it's conservative. Yep. So if curl of F is equal to 0, then F is conservative, F is a gradient field, the integral of F is path independent. Yeah, there's a whole list of that, remember? Let's bring out that list again. So here's our list that was applied to in, or was brought up when we were only looking at these vector fields in 2 dimensions. So, I'm sorry, I'm going to take my pen here and change a few things. So our f of x, y, z has components p, q, and r. So f is conservative, f is a gradient field, there exists a potential function. Now we can do these path integrals not only in 2 dimensions but in 3 dimensions also, so this would work. Also for any closed fields or any closed line integrals, this would also work. And then now this was only that special case when we're in 2 dimensions. But if you look at this really carefully, this is the k component of that cross product. But now in 3 dimensions, let's just write that as a curl. So that last bit of information says something about the curl. Okay? So if the curl is 0 of a vector field, then all these things follow, which means we can use the fundamental theorem of line integrals. That's the path independence business. If we integrate over a closed curve, don't do anything, it's just 0. You can find a potential function, and you know that it's a gradient field. Okay? Everything else follows. Okay? Questions? Let's take a look at Green's theorem again. So Green's theorem only works in 2 dimensions. And what we're saying for Green's theorem is that this is equal to some double integral or something, right? In fact, it's equal to this double integral over d. And remember that c is a boundary of d. Of the derivative of q with respect to x minus the derivative of p with respect to y, dA. So the thing is, we're where did this come from, or what is this business thing here doing? And if your original vector field was PQ0, think about this as something happening in 3 dimensions. But it's really happening in 2 dimensions, but let's extend it to 3 dimensions so we can consider it as a vector field PQ0. It turns out that the curl of this vector field is equal to, well, let's do it carefully. Now, I'm going to put P as a function of x and y because there's only x's and y's. There's no z's in there. And you'll see why I'm doing this. So when we take the derivative of, in the I direction, when we take the derivative of 0 with respect to y is 0, take the derivative of q with respect to z, but like I just mentioned, there's no z's in there. So that's also going to be 0. Derivative of q with respect to z is equal to 0 because there's no z's in there. And so we're going to get the same thing for the next term. So throw a negative there if you want. But the last term, this is k. The last term is going to be the derivative of q with respect to x minus the derivative of p with respect to y. And you see that that is just the double integral integrand in Green's theorem. So it turns out that the second integral, or the double integral in Green's theorem, can be written like this. It's the integral of d of the curl of f This curl has a 0, 0, and something in the k component. How can I get rid of that k component? How can I make this not into a vector? With what? No. Dot it with k. 0, 0, 1. If you dot this with 0, 0, 1, you get exactly that. This is Green's theorem in vector form. There's nothing new here. It's just Green's theorem, but we're writing it in a slightly different form, in a vector form. K is just 0, 0, 1. So imagine dotting this curl and this vector 0, 0, 1, and that's exactly what you would get here. Say it again? The unit vector 0, 0, 1. Yeah. So it looks like the integral of a derivative is actually equal to one less integral of the original function evaluated at the boundary. What? I have a double integral here. Double integral, and I have a derivative inside. Double integral of a derivative, and I'm integrating over some region. Integral of a derivative over something is one less integral of the original function at the boundary. Let's put a circle there just for kicks. Okay. So basically I want to say the integral of a derivative, in this case our derivative is the curl. The integral of a derivative over a region D is equal to one less integral of the original function over the boundary Oh, I can't do that shape. So remember that yesterday they introduced this new symbol. Well, it's not a new symbol because we've known it as the partial of something, but now they apply it on the geometric region. That means it's the boundary. Yeah.
Isn't that just a line integral all over again?
Well, that's what Green's theorem says.
Right, so we just undid Green's theorem into what we already did.
Well, I'm just showing equivalences here. We're not doing or undoing. That's the thing about these theorems. Although Green's theorem is probably not a good example, but these theorems have two things that are equal to each other. And later on, you'll see that the two things that are equal to each other are working together. It doesn't mean that each problem is going to depend on which one of those sides is going to be easier to compute. So there might be sometimes in the worksheet that you guys were working on, it turns out that a lot of times a double integral is easier to compute than the line integral. So that's what we did. We computed the double integral. We'll see later on that between the two sides of an equation that you have, turns out that one way might be really hard to impossible to compute, but if you do the other side, then it would be a lot easier. And it depends on the situation that you have. Yeah?
For the closed, the boundary D, the closed FDF, do you need a dot product between those?
Yeah.
So I was just saying,
Yeah, that's the same.
Yes, DR.
That's what I was saying. Same
Oh.
thing.
So this is just fundamental theorem.
Green's theorem is just the fundamental theorem of calculus. Yes. In fact, the next big theorems that we're going to be looking at are all just fundamental theorems of calculus. What is the fundamental theorem of calculus? Fundamental theorem of calculus, you're integrating over an integral. You're integrating over an interval, a to b, right? So what if I just change the notation a little bit and say, let's integrate your f. Let me rewrite that. D, not even a straight D, because f is only a function of x. Over an interval, I. So the integral of a derivative is equal to one less integral. There's only one integral, so one less integral, it means the integral is gone, of the original function evaluated at the boundary of the interval, evaluated from a to b. That's the boundary of the interval, boundary of the interval. So the integral of a derivative over a region is equal to one less integral of the original function over the boundary. That's the original fundamental theorem of calculus. And now we're going to have a bunch of other versions of the fundamental theorem of calculus, but then they'll just look different because we have different integrals now. We have double integrals, triple integrals, line integrals, surface integrals. Surface integral. Wow, how's this? All right, let's take a look at an overview of the integrals that we know so far before we meet new ones. So integrals so far. This was a nice one, right? Let me rewrite this. Is this okay? You understand this. I is the interval from A to B. Right? And I want to put a special case over here. Which is kind of silly for this, but if we integrate 1 dx, what is this going to equal to? The length of the line segment, the length of the interval, length of I. Right? All right. Now we have the double integral, right? We studied the double integral. What if I scratch out this f and take the double integral of 1 dA? Do you remember what that one was? That's the area of D. Right? The triple integral, I think we use E. If we put 1 in for the integrand, what do we get? Right? What else did we do? Line integral. Well, R or S? So this is, people call it a line integral if they want, but I like to call it a path integral because, oh yeah, let's take the arrow out. So I want to differentiate the idea of integrating over integrating a scalar versus integrating a vector field. So this is a scalar. And that's because I want to consider what happens if we put 1 in for this. So what do you think happens? What is a path integral when we integrate over a curve of just 1, the scalar function 1, arc length? Okay, and if you want to recall, the ds is actually the magnitude of r prime once you get the parameterization going, then you know that the integral of the magnitude of r prime is just the arc length. Okay, so these are special cases, and we'll see that we'll add one more to this list when we're going to do a double integral over a surface, a double integral of a scalar function. So there's 2 more integrals that we're going to consider. And I use a capital S for this. Well, that's why I wanted to use R for the other one, is because this is S. And little s and big S, I want to make sure that there's a difference between little s and big S. So there's 2 more integrals. One we'll call a surface integral. By the way, I think the book calls both of them surface integrals. Yeah. Actually, the book calls this a flux. But they consider a flux as a surface integral. I'd like to keep them separate, but, you know. So these are the last 2 integrals that we're going to consider. But before we do that, look at this. We're integrating over a surface. When we integrate over a curve, we have to parameterize a curve. We're going to need to parameterize surfaces. So
We're so good at the curves, though.
you guys are really good at the curves now. Now you're going to have to learn surfaces. So we'll need to parameterize surfaces, and then we'll look at the geometry of the surface integrals, and then look at the geometry of the flux. All right. Wow, this looked really hard. I mean, looking at you was hard for me. So study hard.